Welcome to this fifth lecture on logic. Now that we're comfortable with propositional logic, let's step back and look at the strengths and limitations of that system of logic. Well, the strength is pretty clear. We already showed we can use propositional logic to formalize arguments and then to prove that these arguments are logically valid. So, in this segment, we're going to try and identify some limitation of propositional logic. And to do so, we will consider this argument made up of three sentences, S1, S2, and S3. Now, first of all, this is not really an argument. S1 and S2 and S3 by themselves do not make up an argument. They're just three independent sentences. Now, the reason I call this an argument is I'm going to claim that S3 is a logical consequence of S1 and S2. In other words, the argument appears when we insert the word therefore in front of S3. So what I claim is that S3 logically follows from S1 and S2. Now remember what that means. That means whenever both S1 and S2 are true, then S3 must also be true. This is slightly different from the previous arguments we saw before because it has two assumptions or hypotheses. We assume that both S1 and S2 need to be true to prove that then S3 must be true. Now, how are we going to prove that this argument is valid? Well, the first step is actually to convert the English sentences to propositional logic. And then we can ask ourselves, is it really the case that S3 logically follows from S1 and S2? And the easy way to answer that question is to build a truth table for S1, S2, and S3, then look at all the rows where S1 and S2 are both true, and check that in all of these rows, S3 is also true. And that would prove that the argument is valid, right? But before we do all of that, let's just think about this argument in a non-formal way and try to determine for ourselves whether it is actually valid. Well, the answer is, sure, this sounds completely valid, right? If all dolphins are mammals, and Flipper is a dolphin, which follows from S2, then clearly S3 must be true. Flipper is a mammal. Okay, well, this is just an intuition. Let's prove it. The first step in proving the validity of the argument is to convert its English statement into logic. So let's start with sentence S3, since it's the shortest one. Flipper is a mammal. It is a declarative sentence that's either true or false. Can it be decomposed into smaller propositions? Doesn't look like it. It does not contain any logical connectives. So let's conclude that S3 is an atomic proposition. Let's denote it with logical or propositional variable P3. Okay, let's go back up the list and consider S2 next. Is S2 a proposition? Well, the first thing to look at is whether it's a declarative sentence that's either true or false. Does look like it. Next, we got to worry about whether we can decompose S2 into smaller propositions. Well, let's see. S2 does not contain any logical connectives. So it does look like it's an atomic proposition. Let's call it P2. But here, it's a good idea to stop and think a little bit more. So for example, what are the possible ways that one could make S2 turn out false? Let's say Flipper is a male dolphin, then clearly S2 would be false. But because Flipper would still be a dolphin, part of S2 would actually still be true, and the other part of it, the part about being female, would be false. So what that indicates is that even though S2 does not contain a logical connective or the word and, it is actually the conjunction of two atomic propositions. So let's call these propositions F for Flipper is a female and P2 for Flipper is a dolphin. So the final translation, the correct translation of S2 into propositional logic is the conjunction F and P2. Finally, let's convert S1 to propositional logic. Since S1 is a declarative sentence that's either true or false, it's definitely a proposition. And since it does not contain any logical connectives, and it's not obvious how to break it down into sub-propositions, let's say it's an atomic proposition, and let's refer to it with propositional variable P1. Well, actually, it's another good time to stop and think, right? This is another example where the structure of the sentence is much more complicated than it appears. In particular, if you look at S1, you'll realize that it's really talking about two kinds of objects, something being a dolphin and something being a mammal. And in fact, it's making the claim that whenever something is a dolphin, then it's also a mammal. So really, S1 is not an atomic proposition. It's another one of these examples of hidden conditionals. So let's get rid of P1, and let's use the propositional variable D to refer to something as a dolphin, and let's use the propositional variable M for something is a mammal. And you should think about whether this makes sense to you, but I claim that the translation of all dolphins are mammals is something like this. D implies M. If you're a dolphin, then you're definitely a mammal. Notice the implication doesn't go the other way. It's not true, at least S1 does not claim that every mammal is a dolphin. Just the other way around. Now that we formalized the argument into propositional logic, let's move to step 2, which is to prove its validity using truth tables for S1, S2, and S3. The first step in building the truth table is to determine the number of distinct atomic propositions involved so that we can determine or compute the number of rows in the table. Well, there are 5 distinct atomic propositions, D, M, F, P2, and P3. So how many rows are we going to have in a truth table? Holy smokes. 32 rows, right? 2 to the 5th power. That sure is a big table. That's going to be a lot of work. So maybe before we start building the table, we should stop and think. In fact, you should realize there's something strange about this set of 3 propositions. Notice, for example, that P3 only appears inside S3. It does not appear inside S1 nor S2. So intuitively, it seems impossible that S3 is going to follow from S1 and S2. How could you infer anything about P3 from S1 and S2 since neither one of those sentences even refer or contain P3? So maybe instead of building the truth table to show that the argument is valid, maybe we should look for a counterexample. In fact, it's very easy to find an assignment of truth values to the 5 propositional variables that make S1 and S2 true and S3 false. How do we make S2 true? We want to have a choice. We need to make F true and P2 true. And then to make S1 true, an easy way is to make D false. So now that we have S1 and S2 true, it's very easy to make S3 false. Just pick or assign the truth value of false to P3. And the truth value of M doesn't even matter in this case. So what this means is we just found an assignment of truth values to the 5 atomic propositions that actually make the argument invalid, because we just found a situation where S1 and S2 are both true, but S3 is false. So actually, it looks like the argument is not valid. Now, a couple minutes ago, we reasoned in an informal way, just using intuition, to convince ourselves that this argument is actually valid. But now that we converted it into logic, we just proved that this argument is actually not valid. So what's going on here? Well, either our intuition, our original intuition, was wrong, or we made a mistake when we converted from English to logic, or both. So we got to figure it out. So I suggest that we actually review the logical conversions we performed, because I still claim that there is something highly suspicious about this set of propositions. Again, notice how P3 does not appear in S1 or S2. So how could anything be inferred about P3 just by knowing that S1 and S2 are true? Now, let's see what would happen if we change the propositional logic formulation in the following way. Let's say we replace the proposition for S1 from D implies M to the other conditional P2 implies P3. Now, why would that even be a good idea? Well, because at least now P3 appears inside S1. So it has a direct connection to S3. Okay? In fact, it's not too hard to see that if S1 was translated this way, then the argument would become valid, because if S2 is true, that means P2 must be true. And if on top of that S1 is true, that means this is true. That means every time P2 is true, then P3 must be true. And since P2 is true from S2, we could easily infer that P3 is also true. Now, even though this second translation of S1 appears to make the argument work, we still have to check that it actually makes sense by going back to the English translations of S1. Turns out this conditional in English doesn't mean the same thing as this one. So let me make sure I convince you of that. So what does P2 mean? Well, we don't have a choice. P2 was introduced here to mean that Flipper is a dolphin, whereas the meaning of P3 was introduced here, namely Flipper is a mammal. So in other words, the English translation of this conditional is, if Flipper is a dolphin, then Flipper is a mammal. And that is not at all the same meaning as D implies M, which was, remember, if something is a dolphin, then it's also a mammal. Sounds like this statement is much more specific than this one. So for example, let's look at the meanings of D and P2. What is different between those two propositions? Well, P2 states that Flipper is a dolphin, whereas D states that something is a dolphin. In other words, P2 is a special case of D. This its meaning is. Its meaning is much more specific. It only says something about the flipper, a particular object, whereas this D here refers to any object that happens to be a dolphin. So, even though this new argument, including this conditional, appears to be valid, it is not a correct logical translation of this argument because P2 implies P3 is not an appropriate translation of S1. All dolphins are mammals is completely different from if flipper is a dolphin, then flipper is a mammal. It almost seems like we introduced the proposition that we needed in order to prove the conclusion. That's exactly what we did. Now, here the problem is there is no way to actually convert this argument into propositional logic. It's a main limitation of propositional logic that I want to highlight in this segment. So the main limitation of propositional logic in this context is that it is too coarse-grained a representational scheme. In other words, it's not able to represent enough details about the English statements that we're dealing with. So here is what I mean. Remember that D stands for the statement that something is a dolphin, whereas P2 stands for the statement flipper is a dolphin. Those two propositions are different, and therefore they must be represented by different propositional variables in logic, in propositional logic. But what propositional logic fails to do is to represent the fact that these two statements are very similar. In fact, the only difference between something is a dolphin and flipper is a dolphin is the subject of the sentence. The verb phrase is the same in both cases, is a dolphin. The only difference is that the subject is something general in the first case, and flipper is the subject in the second case. So the main problem with propositional logic here is that it's not able to represent this level of details. It's not able to go inside the propositions and to realize that some propositions have the same verb phrase and only differ by their subject. And the reason for that is, by definition, propositional logic does not go below the level of propositions. Every propositional variable represents a full sentence. So it's not able to represent the fact that even though two propositions are different, like these two, they are also strongly related. And this is the kind of detail, quote unquote, that we need to prove that this argument is valid. In particular, we need to be able to represent the fact that flipper is a dolphin is a special case of something is a dolphin. So I hope that this first segment has convinced you of at least some of the limitations of propositional logic, which we're going to use as a motivation to introduce a slightly, or actually significantly more powerful system of logic.